Okay, new unit. Working with radicals. So this unit is all about radical expressions and equations. Radicals are everything with the square root sign. That's our fancy word for things with roots in them. Um, Radicals, I think, can be a very intimidating concept at times, and I think a lot of people are scared of them, at least at the beginning. But there's actually only a few rules that actually deal with radicals, and once you learn the rules, then they're really not that bad. You should be able to keep them all in your head, and with enough practice, then you can get very, very comfortable with them. A lot of people, when they start seeing things with radicals, they do kind of freak out at the first and they don't know how to simplify these things. But they're really not too bad, as evidenced by there's only actually 3 lessons in this entire unit. So we're going to be able to move through it pretty quickly. There were two kind of warm up sheets before this one, and if you didn't get a chance to work through them after the test, which I think was pretty much everyone, maybe Pavel got somewhat through it, you should probably try and work through those over the break and come and check all your previous understanding of these things. Okay, let's start. So in this one, we're going to start talking about the first big rules for it. First, how do we name these things? So these have special names we don't use that often. We use radical, we use root very often, but there's some specific ones. The M is called the radicand. The N is called the index. Just think of it like a book. It's got like the index number. It tells you generally what kind of a book you're reading. I like to think of it like that. An A is a coefficient. So we should be very comfortable with that. And then a radical is basically the whole thing. So if you take the entire thing, it's one big radical, or a root, we sometimes say. So radical kind of refers to the whole thing. Um, and people don't use these words very often. If we're trying to be picky and we're using it in the unit, we will. But in general, like when you get into grade 12, usually we just use these ones. We just call them, we're only talking about the whole thing, the radical, the root, and we say, oh, what's inside the radical or something. But we should get comfortable with these languages because we're really going to analyze them in this section. Okay, now the rules. Simplest form, I also call it like good form. I don't like that they always call it simplest form. Sometimes in math, it's not very clear what's actually the simplest form. We always say, oh, simplify it as far as you can go. But sometimes there's multiple different places that seem like a very simple version to leave it at, and you're not really sure which one you're looking for. So it's not necessarily the simplest form that we're looking for. It's actually good form that we're trying to do. We have a set of rules that we always like to adhere to. That way our equations look generally the same. That means that we're not going to be tricked by them. That means that we can compare them to each other. And that means that we can do further math with them in a pretty efficient way. So we generally look to try and have good form. Now with radicals, this means a couple different things. And we have our 3 rules right here. So rule number 1, the radicand does not contain a fraction. So if there's a fraction in here, we're going to actually simplify it. For example, if you have like a over b, we would turn that into root of a over root of b. We can break that down, and that's going to be one of our rules we're learning later today. But we don't like to have a fraction in the radicand. That's not simplified yet. Rule number 2, the radicand does not divide by a factor. This is what you have to have. The radicand must not be able to be divided by a factor, which can be removed. So example, the perfect squares. This is what I always say about look up above the chalkboard at any of those perfect square numbers. Does it divide by any of those things? If it can divide by any of those things, then you're not done. Then you should divide it by those things and pull those out. And we'll be doing that today. And number 3, the radical is not part of the denominator. And we talked about this in our trig unit. You should not have any roots on the bottom. So actually, even in this one, after we got to the step, we would have to get rid of the root from the bottom in this one. So all three of these are our general rules, just to make these things good looking and simple. Comparing and ordering radicals, we don't actually order them very often, but it's a good way of, you want to be able to tell the general size of these things. Radicals, they're not the easiest thing in the world to order, but there's one really easy way to order them. It takes a little bit of work though. So they can be compared using a couple of strategies. Convert unlike radicals into entire radicals. That's actually the best way. This is kind of the go-to way. So put everything inside the radical is what this is saying. If you have an A value, put it inside the radical. If the radicals have the same index, then the radicands can just be compared. Once you've done that, once everything is inside the M, if all the n's are the same, then just the smallest m is the smallest value, and the biggest m is the biggest value. So that's our go-to one. If they are like radicals, which means the n and the m are the same, that's what we're going to mean by a like radical, then all you have to do is compare the coefficients. So then only the a will matter if both the n and m are the same between different radicals. So that's not going to happen very often though, but sometimes it will. Number 3, you can compare the indices of radicals with equivalent radicands, with equal radicands. So if the m is the same, then you can just compare the n value. The smallest n value will be the biggest number, and the biggest n value will be the smallest number. If I'm pretty sure that's right. Yeah. Okay, let's try some examples. Oh, and actually, one more definition thing we need to talk about. Radicals have one really important feature to them, and that is you can never take a radical, you can never take, say, the square root of a negative number. And we've talked about that before. So we haven't had a lot of things with super restrictions, with very important restrictions, but this one is a very significant one in mathematics, and we always have to be mindful of it. So the way we say this, if the index is an even number, anybody know what the index is of this one? This would have been a good question for live. A square root is actually an index of 2. There's always an implied 2 there. And there could be any number there. It could be a 2, 3, 4, 5. It could be any kind of a root. A square root is the second root. So every time the index is an even number, the radicand must be positive. You are not allowed to have a negative number. You are allowed to have 0. 0 is okay, but negative is no good. Any kind of negative is no good. And that doesn't just apply to square roots. Square roots are the most common, but it's actually every single even root. So a 4th root, a 6th root, an 8th root, any even number there, and this is no good. If the index is an odd number, then this actually doesn't apply. Both positive and negative are good. There's no rules against odd numbers. That's nice. Okay, moving on. Already 8 minutes in. This is the fun part. Express each entire radical as a mixed radical. So this is our simplifying it based on rule number, I forget which one, 2? Yeah, rule number 2. So if you can pull out any of those perfect squares, we're going to try and pull it out. So what does 200 divide by? Up in those purple numbers above the chalkboard. The biggest one it divides by, it could divide by a lot of things. I think it divides by 4. It divides by 25, but the biggest one is 100, which is great. So we would actually say this is the same as root of 100 times 2. So we break it down to the product because the 100 is a good number. We can take the square root of 100, which means it's going to be, square root of 100 is 10, but the 2 we couldn't deal with. The 2 is still left there behind. That's basically it. You break it down multiplication, and then you do the square root of each side separately. And this side was just nice, and that side was still ugly. Okay, next one, 52. which number does that divide by? The biggest one for this one is going to be 4. So we would say it's equal to negative root of 4 times root of 13. Because 4 times 13 gets to 52. So you're not subtracting 4, you're not dividing by 2, you're dividing by 4 to get to the thing left behind. Now, root of 4 is just 2, so it's negative 2 root 13. I think this part's actually fun. I think some people kind of stress about it, but I think this part is actually not too bad. Variable this time. It was a little bit hard to see. I could maybe kind of bring this down a bit. Okay, a variable, the 4th root of c to the 9. So actually, every 4 variables we can pull out and have one variable on the outside. So we could actually write this as the 4th root of c to the 4 times the 4th root of c to the 4 times the 4th root of c. Now I know you're probably saying, hey, that seems like a lot of numbers. I thought you said we had to divide, not subtract or anything like that. It's because it's the exponents that are changing. So if you multiply these, you actually just add the exponents together. C to the 4th times c to the 4th makes only c to the 8th, times c makes c to the 9th. So exponents are just subtracting or adding when you're dividing. So 4th root of c to the 4th is just c. The second one is also another c, so there's actually a c squared on the outside, and a 4th root of c still remaining to go. So try it with the next one. You probably could pause at this point and try the last 3 on your own. They're a bit tricky, that's for sure, but hopefully you can do them. Okay, this guy will be, I'm not going to do it in the full version. So every 3 I can pull out, and it's 1 on the outside. So 3, 6, I can pull out 6, and that's going to be an a squared on the outside. And that leaves me with a single 3rd root of a left behind. So you don't have to write every step every time. If you can kind of figure it out, that's okay. Even here, I don't know if it's completely necessary to write the middle step. If it's kind of a hard one, it's probably good. If it's an easy one, you can maybe just jump right to the answer. 48. So now we have to do both things on their own. What's the biggest number 48 divides by? 16 is going to be it. So this is going to equal the root of 16. I'm going to do this one a little bit slow, just so we're sure. And it's going to equal the root of y to the 4th. And what was left behind? 3 and y. Because 3 times 16 makes 48, and y to the 4th times y makes y to the 5th. Now the first 2 things can just be given as numbers. So that's 4 y squared and 3y on the back. Okay, last one. First thing we got to do is take it 3rd root of the top and 3rd root of the bottom. I always say the negative belongs to the top number. So negative 40 if you have to make it belong to something, I always treat the negative as belonging to the top number. I'm pretty sure that's always the right way to do it anyway. It doesn't actually matter which one you make it belong to, but it's good practice to make it belong to the top one. Okay, what does 40 divide by? Well, it divides by 8. Oh! That's the tricky part. We haven't actually done this yet, have we? Every time we've had a coefficient so far, it's always been square root, square root, square root. Now this is a 3rd root one. So this is actually going to change some things. We're now looking for cubic numbers that this divides by. So we're actually looking for, there's another set above my chalkboards on the right side now. We're looking to see if it divides by any of those numbers. That's the one way to do it, and that's the easier way to do it. It's pretty hard with cubic roots. There is another way to do it. I think I'll show you guys maybe after the break how to do it with the prime factorization way. I don't like the prime factorization way, but for higher roots, it might be a little bit more useful. And for really, really big numbers, sometimes it's useful. So, cubic roots, the numbers that we want is actually 8. So we're going to say that's 8 times 5. And the negative actually doesn't bother us. We can treat the negative as with the 8 because you can do the third root of it. So we're going to pull out -2. The third root of 8 is actually 2. So the third root of -8 is -2. And we leave the third root of 5. Okay, what number divides 81? Well, that's going to be 27. What cube root divides 81? That's 27. It should be 27 times 3, which means that we're going to pull out the cube root of 27, which is just 3, and we left behind 3. Good. That's pretty much it. Oh, I forgot the 3 there. Third root, not square root. Did we actually satisfy all of our rules? We don't have a fraction. It can't be simplified. We're still breaking the third rule. We haven't simplified the denominator. We're going to do that in another lesson, so we're going to leave that for today. But eventually we're going to rationalize the denominator as well. Okay, moving on. My calculator can sense what's going on. Okay, this is the easiest part, I think. Can you go the other way? Can you take a mixed radical and put it back into the radicand? Most people are pretty good with this one. It's actually not too bad. So in order to get 7 back inside, you need to put it inside a square root, which means you actually have to square it. So going nice and slowly, we would actually say this is the square root of 7 squared times the square root of 2. Where's my calculator? So 7 squared is equal to 49. So that's going to be root of 49 times 2, all under the same square root, if you want to do that. And that is 49 times 2, 98. Now that was the full-on slow way. We can do this a little bit faster. So all we have to do is say 4 squared times 3. 4 squared times 3 is 48. So that one is all just going to be the root of 48. Okay. This one, now the exponent is actually going to get bigger. So it's the same thing. It's going to be a to the 4th squared. And hopefully you remember your exponent rules. A to the 4th squared means you have to multiply those two numbers together. So power of a power means multiplication. So that's going to be a to the 8 times one more a is a to the 9th. So the square root of a to the 9th. I don't like the autofocus on this thing. We have to figure out a better way to make it stay focused. Okay, this guy. So now we need to pull the 5b inside a cube root. So it's still not too difficult. Let's do the coefficient. Let's try and do this all in one step. Which means I've got a big cube root. So for the coefficient part, I'm going to do 5 cubed times 3. So 5 to the power 3 times 3. is 375. And then we do, that's just a single value of b. So b cubed times b squared. So multiplying two b values means adding their exponents. So b to the 3 times b to the 2 is b to the 5. Hopefully that makes sense. Okay, and then this one is, so we have to pull a -2 inside. And you're actually not allowed to do that. So this guy has a special rule. Even though we want to pull the -2 inside, you can't actually pull the negative inside because there's no way to get the negative onto the inside. So we actually have to leave the negative on the outside, and we're just going to take 2 to the power 4. So 2 to the power 4 is equal to 16. So this one is going to equal negative root of 3/4 times 16, which is negative root 16 times 3, 48 over 4, and that should simplify. Actually, does that divide right away? It does indeed. 12. It's actually just 12. 48 over 4 is 12. Or you can do your cross canceling, is actually the best way to do that one. So negative root of 12. Good. Did we answer the whole question? Identify the values of the variables for which the radical represents a real number. So is there any restrictions on these questions, the ones with variables? The ones with numbers, obviously it just works. What about this one? If it's a to the power 9th, it has to be square rooted. Well, we know a to the 9th has to be positive or equal to 0. Positive or equal. So when is a to the 9th positive or equal to 0? Well, you can take the 9th root, and all that says is a has to be greater than or equal to 0. If a is positive, the question will be positive. If a is negative, no good. Then it'll be the whole radicand will be negative, and so the whole thing will be unsolvable. What about in this one? So we're under the square root sign, but it's actually the third root. So there's no rules in this one, which means b can be any real number. It doesn't matter if b is negative. You can have this number in here negative. It doesn't bother us because you can take the third root of it still. No rules when it's an odd radical. And then this one, there's no problem with that. It's just numbers. Okay. The problem was you have to leave the negative on the outside. You weren't able to bring it inside. Compare and order radicals. So can we actually use what we know about comparing them? The first one's really, really easy. So we have third index of 3, third index of 3, third index of 3. So we can just compare them with the coefficients. So the smallest, does it say, oh, greatest to least. So greatest is going to be 8. 8 third root of 3's. Then it's going to be 7 third root of 3's. Then it's going to be 3 third root of 3's. Nothing wrong with that one. That one's actually really easy. Compare all these ones. Okay, this is a bit harder now. The problem is, well, we have a lot of different things going on here. First, we have an exponent to the half. That's the same thing as the square root. So this is going to be the square root of 13. Start simplifying it a little bit. This one looks fine. This is just a whole number. This one kind of looks fine, and this one's a mixed one. So mixed, entire, whole number. And we need to have some way of comparing all these. So we actually want to turn them all into entire radicals. If all of them were entire ones, then we can compare them. Not too bad. Because they're all the same index. They're all square roots. Or they could be all square roots. So let's do that. 4 squared times 13 is 208. So that is the square root of 208. 8 squared times 3 is 192. What do we do with the 14? Well, we can still square it and put it under the square root sign. There's actually no problem with that. It's a pretty easy question. You just have nothing to multiply it against after. So this is actually going to be the square root of 196. Root of 202 is just root of 202. And then 10 squared times 2 is 200. Yeah. There. Now we should be able to compare these pretty easy. I'm just going to number these ones off. Does it say least to greatest? Last time it said greatest to least. So greatest, 1, then 2, then 3, then 4, then 5. The bigger number is the bigger number. It's kind of that easy. Okay, last question in this section. Determine where a radical is defined. So we did 1 or 2 questions like this in the last section. Now we're really trying to focus on what are the restrictions on these. Restrictions are going to be a bit more of a 20-1 question, but at least the simple ones and a basic understanding of this is expected from my 20-2 people as well, because it is a big part of the unit and you need to be able to understand the nature of the restrictions on roots. So for what value of the variable is this a real number? What value of the variable is allowed, basically? So square root sign, so we are going to have a restriction, and the restriction is the thing under it, 54 x cubed, must be positive. So this is going back to our inequalities. We saw these in grade 9 and a bit in grade 10 as well. So we need to be able to solve this, and then we will state our variable. So divide by 54. Doesn't do anything. Cube root it. Doesn't do anything. And that's it. If x is positive or 0, the whole thing will be positive or 0. So that's not too bad. Second one. Same thing, it's an even index, it's 2. So the rule is 4 minus x must be positive. If it's not positive, it's no good. If we call it 0 positive. Now, solving for this one, so we're going to subtract 4. And that one's just fine. And now we have our only special rule for inequalities. Inequalities just operate like equal signs most of the time, except for this rule. Now we have to divide by -1, which means we have to flip the sign. So it's going to be x and 4 when we divide by -1, but now the sign goes the other way. When x is less than or equal to 4. And we should check just to make sure that's true. So this says that it's okay when x is 0. So if I subbed in 0, 4 minus 0, yeah, that's a positive number. That works. This says it's not okay if x is 5. If I subbed in 5, 4 minus 5 is a negative number, so that's true. So it seems to work. C, third root of a number. Well, doesn't matter. Odd index, no restrictions. We like those. Except that they're harder to simplify and they're harder to graph, and so we don't actually like them. But we like them when it comes to restrictions. Square root of 27x squared. So 27x squared has to be positive. Divide by 27, square root. So as long as x is positive. Or is it? This is actually a bit of a funny one. So let's take this one slowly. I divide by 27, so I have x squared is greater than or equal to 0. And now we actually do two things, remember. If there's the square root sign, it ends up with that funny plus minus value ends up coming in here. Sorry, I was just looking at the answer for this one. I have an answer key beside me, and it actually got this one wrong. Yeah, that's actually kind of funny. So when is x squared greater than or equal to 0? Actually, this is always the case. X squared will always be a positive number because whatever you put in there, you're squaring. And it's a little bit difficult to explain algebraically. Because if we do it the way that we kind of know, so you would take the square root plus and minus, so you'd say x is plus or minus 0. That doesn't really help us. That doesn't actually solve it. So the way we were doing it isn't actually a great solution. The better way to do it is this. When you take the square root, I'm going to do the really thorough way. This is more for the 20-1s. So we say x squared is greater than or equal to 0. And we take the square root of both sides. So that's just fine. You don't actually have to write the plus or minus thing. But then the answer to this, the square root of x squared, is actually absolute value of x is greater than or equal to 0. And then you can break it actually down. Because this has two possible answers when x is positive and x is negative. Actually, I don't think I'm going to get into the full detail about this one. Because it is actually a bit of a hard concept, and I don't think I can explain it. It would take me like a good 10 minutes. Maybe I'll talk to you, maybe at the end of class, I'll go over this one with you. But the idea is, x squared greater than or equal to 0 is always the case. There's nothing you can sub in to actually break this. So this is actually all real numbers. And you could try that. If I subbed in 0, the whole thing will turn into 0, so it's fine. If I subbed in -1, -1 squared is positive 1, so it's positive. If I subbed in positive 1, obviously it's the same thing, it works. So it actually works for all numbers. That's a bit of you have to kind of understand this absolute. We don't know anything about absolute value x yet, so it's a bit of a tricky one, but you should be able to get it from here. So when is x squared greater than or equal to 0? And it seemed like you should have just gotten that half answer, but it's actually the whole thing. It's all real numbers. Okay, sorry, last one. Fourth root of -12x cubed. So this one's a little bit different because we got the negative on the inside. That's okay as long as the whole thing isn't negative. So we still have an x to sub in. So the rule is -12x cubed has to be positive. You can't have a negative under that fourth root. So I'm going to divide by -12, which is still 0. So we have x cubed and 0, but I divided by a negative. So I have to flip my sign now. So we're actually looking when we have a negative x value. And if you cube root it, that happens when x is negative. Good. That's it for this one. This guy is special. I'll try and give a full explanation of that at the end of class for those who's interested. I think the best way, my full explanation probably isn't going to be what you're going to use every day. The best way is just to recognize it from here. So when you get to this point, realize that x squared is always going to be a positive number. So it's actually fine. The full explanation is actually, yeah, it's a bit weird. But we'll do it anyway, if you're interested. Okay, we're going to do part B today as well. So you can either spend a bit of time doing some questions right now and then watch B, or you can watch B right away.